Right, so I mentioned ice albedo feedback a few times. As I said, it is one of the most important feedbacks in the system and has operated very effectively for a long time. Feedbacks are important because they can amplify or damp the initial perturbation, right? This is why we care about them. So the forcing or the perturbation itself in the radiation from the orbital changes, for example, may not be that big, may appear small, or the change in CO2 or something may appear small, but if there are amplifications of that perturbation in the system, then you have to really be careful. And one of those is shown here. This is a record that we mentioned several times, but didn't look specifically in this form before. So time again is going from 800,000 years ago to the present from left to right. And on the vertical axis you have temperature, carbon dioxide, and methane. Three curves, right? So let's focus on this first. What do you see here? So you see a temperature change that looks kind of abrupt on one end and then slower on the other end, especially if you come closer to the recent times. So you can see there's an abrupt increase and a slow decrease. Abrupt increase, remember these are anomalies from the reference period. So it's warming abruptly and cooling slowly, warming abruptly and cooling slowly. And this is approximately on a 100,000 year time scale, which we have mentioned several times. Methane and CO2 are doing a similar thing. They are increasing abruptly when the temperature increases, and they are decreasing slowly as the temperature cools down. And the other point to note here is that in the recent period, or the last couple of 100 years, we have increased this tremendously. So methane has gone from here all the way to here in ppb, as we saw from down at 400 ppb at the end of the last ice age, to now over almost close to 1800 ppb, maybe getting close to 2000 parts per billion by volume. CO2 has gone from being maximum of around 280 parts per million by volume in the warm period to down to 200 parts per million by volume during the ice ages, to being over 400 at this point. So we have gone beyond any change we have seen in the last 800,000 years, and there are other evidences that combine this and say we are at the highest greenhouse gas concentrations maybe in the last 20 million years. Why is that important? Because when you look at the temperature change is not jumped up quite like the CO2 and methane changes. So we have a little bit of explaining to do here, right? Few things to be explained are: why is the warming relatively abrupt compared to the cooling? Cooling happens on 100,000 year time scale, whereas the warming appears to happen very rapidly in literally 100 year time scale. And why is there such a sharp jump in greenhouse gases but not an equivalent jump in temperature compared to, I don't know if you heard, the chopper went by. Some politicians flying around, I'm sure. Or maybe a movie star. We are in Bollywood after all. Right? So, let's do one thing at a time. The changes here are caused by orbital forcing because this is before human activities. So this is natural variability. 100,000 year time scale, as we said, could be related to changes in ellipticity, but we said that change is usually not very large, even including the feedbacks. But precession and ellipticity changes can combine to produce a resonance at this kind of time scale. So whatever it is, it's orbital forcing. When warming happens, it can go very rapidly. Why? Remember we said radiation change at something like 65 north could be important. This is in Antarctica, so we are in the south. This is the Vostok ice core over Antarctica, where the glacier is several kilometers thick, so it records a long time history of climate change. So slight increase in incoming radiation can begin the process of warming and retreat of the glacier or reduction in the glacier extent. That leads to a reduction in albedo, which results in more energy absorption by the system because the reflection of the solar radiation is reduced. And then more glacier melts because you are warmed the temperature further because of this positive feedback, and boom, you have this accelerating positive feedback, and you have what are called abrupt climate changes. Okay, very rapid change because of the positive feedback. Why is it warming slowly over time? Because remember, if the radiation perturbation is now going back to reduced incoming energy, this is going to make the temperature cooler. This is going to make the glacier growth favorable. But how is the glacier growing? It's growing by snowfall that doesn't melt in the winter. More snowfalls gets compressed into glacier. But if you're cooling, then you are reducing the water vapor in the atmosphere. So the snowfall rate gets smaller and smaller as the temperature gets colder and colder. So the ice albedo feedback is still working, in the sense increased glacier extent is going to increase the albedo, increase the reflection of shortwave radiation, so cool the temperature further, and should continue to grow the glacier, except that the glacier growth becomes slower and slower because the drying of the air with the cooling continues to reduce the water vapor content overall, reduce the snowfall rates, and reduce the rate of glacier growth. So it's a positive feedback in both directions. In the warming direction with reduced glacier, reduced albedo, more energy absorption, more warming, and so on. But it goes very fast. Whereas in the cooling direction, it is increasing glaciers, increasing albedo, reducing or increasing cooling, but reducing snowfall rate and slowing down the glacier growth. This is why you have this incredibly asymmetric structure in this temperature record and the CO2 record and methane record. Why are CO2 and methane changing? As you change the glacier growth and you cover the ocean with shelf ice, sea ice, and change the temperature, you reduce the CO2 in the atmosphere. More CO2 remains in the ocean when glaciers grow. So CO2 decreases as temperatures decrease. Methane decreases for the same purpose. You are same process. You're covering more land, you're reducing photosynthesis and carbon sequestration on all those processes. So you're slowly sequestering more carbon and reducing CO2 in the atmosphere. Whereas when the rapid warming happens, the CO2 is going to be belched out of the atmosphere, because out of the ocean and from land, because glacier is retreating. More organic matter that was buried is being exposed for respiration, and ocean circulation is changing as well. So there is about 100 ppm change in CO2, and there is about a few hundred ppb change in methane, but they follow the temperature record. The critical thing to remember here is that the forcing starts with the orbital forcing, warming starts, and then CO2 and methane follow. So temperature leads by few tens of thousands of years. Okay, this is critical to remember. As to why temperature didn't jump up the same way, I will do that in the next podcast by what is called committed warming and so on. Okay, so similar things happened in the recent periods with the medieval warming and the Little Ice Age. There were methane signals, carbon dioxide signals associated with these little perturbations. So ice albedo feedback, very critical feedback, goes very fast in the warming phase and goes much slower in the cooling phase. We are in the warming phase, so we can have rapid responses now with the ice albedo feedback. And this is already evident in Greenland Glacier, which is rapidly melting away. We will see that a little bit later on. Antarctica is a bit more complicated, as it turns out, because it is surrounded by the ocean, the Southern Ocean. We will see that. So remember, ice albedo feedback, very interesting, very important, and very asymmetric in the warming period and the cooling period, but positive during warming, positive during cooling.